Hello, this is David Workman, and I wanted to go through one of my Sudoku puzzles that I've authored, just to kind of show some of the logic that's used in solving some of the non-standard, what's called variant Sudoku puzzles. The variant puzzles are ones that have additional rules in addition to the standard, rules of you just need to put the digits 1 through 9 in every column, every row, and then 3 by 3 box. With the variant puzzles, you have these extra rules that are usually a mix of other types of puzzles or just different rules that have themselves kind of become standard, almost standard rules by themselves, that everybody who solves these type of puzzles understands what these rules are and how they work and what the logic behind them is. But if you've only seen the traditional Sudoku puzzle, then some of these variant puzzles, just seem really, really confusing. So I've published a number of puzzles on the Logic Masters Germany website. Here's a list of all the ones that I've done going back to 2020. So it's been 3 years now that I've been doing this. I go by the screen name Half-Baked Lunatic. So if you just go to the Logic Masters Germany website and search for Half-Baked Lunatic username, then you'll find my puzzles there. But this last one that I've just authored is actually kind of interesting, so that's why I wanted to do a quick video on it. It's really got only two of the variant rules. One is a crop key rule, and then the other is what's called arrows. So the crop key is another type of puzzle where you have a grid of numbers, not necessarily 9 by 9 like a Sudoku puzzle is. It can be, but it can be, pretty much any size or shape. And you have two different types of dots. You have a black dot, which means that there's a 2-to-1 ratio between the two numbers, and then a white dot, which means that the numbers are consecutive. And typically in a pure Kropke puzzle, all of the potential dots are shown. So, you can use the negative constraint, meaning that if there's two cells next to each other, you can be sure that they are not in a 2-to-1 ratio or in a consecutive ratio, or consecutive digits. When you put Kropke dots inside of a Sudoku puzzle, there's kind of a mix. Sometimes all of the dots are shown and sometimes they're not. And so in this puzzle, I've actually authored it so that yes, all the dots are shown and there is only one dot. So it's kind of an unusual layout from the start. With the arrows, it just says that the digits along each arrow must sum to the digit in the circled cell. So whatever this digit is, that must be the sum of these two digits and these two digits, individually, in those two digits and those two digits. So whatever each of these arrows sum to goes into that circle. And really, just from those two clues, this puzzle is solvable. And it might not look like it. I mean, you might look at this and just think it's a complete mess, completely unsolvable. But I wanted to kind of go through some of the basic logic. I'm not going to go through the entire puzzle. I'm just going to kind of show the intro to it and some of the logic. So couple of things about Kropke dots. With the black dot, again, this is numbers that are in a 2-to-1 ratio. So those can either be 1, 2, 2, 4, 4, 8, or 3, 6. So those are the only 4 combinations, of numbers that can go in those two cells. So typically, if you want to go ahead and just fill in all the candidates, that are potentially there, you can do that. I'm going to clear that for now because I'm going to start with the logic behind the arrows. Now, typically with a 2-cell arrow, the minimum number you could have in that arrow would be 3. But in that case, the only two digits you could ever have would be, on the arrow itself would be a 1 and a 2. And you obviously can't have a 1 and a 2 down here as well, because then you'd have all 4, duplicates 1 and 2 in that column, and that, obviously won't work. So if you go up the ladder looking at all the possible numbers that can be in this cell. You know, you can pretty easily eliminate 3, 4, 5. You might think that 6 is possible, but there's only 2 ways of doing 6, and that would be 1, 5, and 2, 4. But there's a problem here. Because of the negative constraint on the Kropke rule, you can never have 2, 4 in 2 cells that are next to each other, because those are a 2-to-1 ratio. And with that negative constraint, that's not allowed. So pretty much the only combination you can have with a 6 is 1 and a 5. So 6 doesn't work. So from there you have the possibility of 7, 8, and 9 as your final possibilities. Now, before we jump into why it might be either 7, 8, or 9, let's look at these arrows coming off that circle. Whatever the 2 cells here that add up to this number, those have to be different numbers than these 2 numbers. I think that's pretty clear, that you can see that, you know, whatever those 2 numbers are, they have to add this number. Those 2 numbers have to add to the same number. But this arrow here, obviously those can't both be red, because when you have 2 reds in this box 1, you can't have a third red of those 2 same numbers. Conversely, they cannot be green, because if you have these 2 numbers adding to that circled cell, then you can't have a third number here as well. So these 2 numbers have to be a different set of 2 digits. And then it's pretty easy to see as well that these 2 can't be either the 2 blue numbers or the 2 green numbers, so they can be the 2 red numbers or anything else. There is no other numbers. You know, you can't have 4 different numbers that add up to any one of these. So, well, actually you could with 9, but I'll show you in a second why that doesn't work. So basically, you have to have 3 different combinations of numbers to make this number that in the arrow cell. Now, if you try to make that a 7, there are 3 combinations of numbers that do add up to 7, and those combinations are 1, 6, which is fine, 2, 5, which is fine, and 3, 4. But there's a problem. 3, 4 is a consecutive number, or 2 consecutive numbers, and again, because of the negative constraint on the Kropke rules, you can't have 2 consecutive numbers next to each other. So that means that with 7, you only have 2 possibilities, and you need 3. And then kind of a similar thing, what's more interesting is with 9, if you want to put 9 there, because 9 seems like the obvious choice. You know, 9 actually has 4 different combinations that you can make up to the digit 9. Those can be 1, 8, 2, 7, 3, 6, or 4, 5. Well, that's well and good, but again, 4, 5 are consecutive numbers, and 3, 6 are in a 2-to-1 ratio. So if you eliminate both of those, you only have 2 combinations that work. So again, that can't be 9. So kind of you can restrict it by using that logic, so that the only possible valid digit here will be an 8. So that's the number that you have, and your 3 combinations for your 8 are 1, 7, 2, 6, and 3, 5. So basically, one of those pairs needs to be in red, one of those pairs needs to be in blue, one of those pairs needs to be in green, and you can work that out. So we're just going to go ahead and put all 3 of those combinations into those numbers. So you have the 1, 7, 2, 6, 3, 5. Okay, great. So now we're going to go back to that Kropke dot. The Kropke dot, again, your pairs that can be are 1, 2, 2, 4, 4, 8, or 3, 6. Well, if this is a 1, 2 pair, you can see pretty quickly that neither red nor blue can be 1, 2, but the pairs of arrows to make up 8 are actually 1, 7. But if you can't have a 1 here, you can't have a 7 either. So if I eliminate 1, 7 and 2, 6 from both of those, then both of those blue and red need to be 3, 4. That doesn't work. That's broken. So your crop key dot cannot be 1, 2. If your crop key dot is 3, 6, you have a similar problem. Again, to make up the 8, if you eliminate the 3, that's actually 3 and 5. If you eliminate the 6, that's actually 6 and 2. So if you eliminate 6, 2, and 3, 5, what have I done here? Oh, I hit 4 there accidentally. That means that both of those have to be 1, 7. Again, that doesn't work. You can't do that. So that basically leaves your combinations that are available of 2, 4, and 8, and there has to be a 4 there. This notation was called Snyder notation. So originally developed by a guy named Thomas Snyder, who when you have the center cells, that means that in that particular cell, that's the only valid digits that possibly could go in those 2 cells. If you put a corner marking, that's saying that within this box, this is box 1 in the grid, the 4s have to be in these 2 squares and can't be anywhere else. You know, so if one of these 2 squares is a 4, the other one's a 2 or the other one's an 8, but the 2 and 8 could be somewhere else. The other 2 or the other 8, you know, if it's not in these 2 squares, could be somewhere else in the grid. So yeah, that's kind of the demarcation between the center marking and the corner marking. Now, let's see. Some reason, I'm not sure how I did this here. I put 4s in these boxes instead of 5s. That's supposed to be 1, 7, 2, 6, 3, 5. Yeah, there we go. Now, once you have that, once you've eliminated the 1, 2 and the 3, 6 combination, this can be either a 2, 4 or 4, 8. There's some logic that you can go through. It's not horribly complicated, but I'm just going to say that there's a couple of different ways you can do it. You can do it by reducing the digits as you go along, or you can do it by just brute force logic. But basically, I'm just going to say that this comes down to the 2, 6 in this row. I just wanted to show that because it makes it it's the other logic up here that I want to show, which is actually quite fun and interesting. So I'm going to go ahead and remove the 2, 6 from all of these cells. And basically, again, the 2 red pairs are the same, whether they're 1, 7 or 3, 5, we don't know yet. And then the blue is the other one of 1, 7 or 3, 5. Now, if you look at those 2 combinations, the couple of things here. So one is because of the crop key constraint of non-consecutive numbers, that could never be a 7 because 7 would be next to 8. So that could never be a 7 and that can never be a 1. And then similarly here, that can never be a 7 and that never can be a 1, which means that you're always going to have 7 in one of these 2 cells. Because again, one of these pairs has to be the 7, 1, the other pair has to be a 3, 5. And that means you're always going to have a 7 in one of these 2 cells, which means that that cell can never be an 8. And I want to show you here because it kind of bounces back and forth. It's actually a really fun piece of logic here. So that can never be an 8 there in that cell of the crop key dot. You can still have a 2, 4 or 4, 8. That's fine. But since this can only be a 2, 4, now you can never have a 3 next to it because whether this is a 2 or a 4, it's always going to be adjacent to a 3. So that further narrows this down. So that can't be a 3. That can't be the 5. That can't be the 3. That can't be the 5. And now you're left with a 5, 7 pair. Now it bounces back the other way. So with this being a 5, 7 pair, this could never be a 4 because one of these is going to be a 5. That's always going to be adjacent to the 4. And now this gets reduced to a 2. Let me clear off that 2. So once you have that narrowed down as a 2, that always can be only paired up with a 4 because of the 2-to-1 ratio. That means that that you've got your 2, 4 pair. So we've got our first 2 digits in the grid beside the first 8 as the arrow. Now, From here, you're kind of on your way. So again, we don't know whether the red digits are going to be 17 or 53 or the blue digits 1753, but we've got to cut it narrowed down a little bit. So to continue, I'm going to fill in some more of these candidate digits in the grid because you need to eliminate some of those to kind of show how the elimination to impact the distinguishing on these pairs. So really the only digits that we have in the grid are this 2, or in this box 1 is the 2, 4. So all of the other digits are 1, 3, 5, 6, 7, 8, 9. That can never be an 8 because it's in that row of the 8. The 4 can never be next to a 3 or a 5. And then we have a 5, 7 pair. I'm sorry, I was misspeaking when I said that. Because of the 5, 7 pair, none of these digits here can never be a 5 or 7. So let's eliminate those as well. With a 5, 7, you can never have a 6 because whether that's a 5 or a 7, you can never have a 6 next to it. So, and again, up here, that can never be a 6 either. So that leaves you with a 1, 9 at the top. And that's kind of important for the next piece I'll go through. Down in this box 4, we have a 2, 6, and an 8. So all of the rest of the digits can be 1, 3, 4, 5, 7, 9. All right, so that can never be a 4 because it's in the same column. Now, an interesting thing here. So, again, going through and eliminating the digits that aren't possible. Next to a 8, the 4 is the 2 to 1 ratio. The 7 and 9 are consecutive. Now, next to a 2, 6 pair, interestingly, you can never have a 3 because 3 is adjacent to a 6 in a 2 to 1 ratio, or adjacent to the 2, a 2 to 1 ratio next to the 6. So that one, and that one can never be the 3. So filling in the rest of this row, we have a 2, 6, and 8 here. I'm going to fill this in. So we have 1, 3, 4, 5, 7, 9 down here. Again, that can never be a 3. So we're going to do a little bit of just regular Sudoku here. So a 4 being here, you can't have a 4 in this column, which means that a 4 has to be in one of those 2 boxes. That also just happens to mean that you can't have a 5 there because whichever one of those is going to be a 4, you can never have a 5 next to it. So that eliminates 5 from being in one of those 2 cells. But it does mean that there is a 4 down here. Similarly, up here, you're always going to have an 8 over here on this side. You have an 8 here, which means that you're going to have an 8 down here. And then a 6 is always going to be in one of these 2 boxes. Again, we can't have it next to the 5, 7, so it has to be there. You have a 6 here. So that also gives you the 6 down here on this side. The 2, you have a 2, 6 pair here, so that's going to give you a 2 here. One of these 3 cells down here needs to be a 4. That means that this one here in the middle can never be a 3. Whoop. I meant to be a 3 or a 5, because that would always be, you'd always have the 4 next to it. If that was a 3 or a 5, you'd always have the 4 next to it. So the whole reason why I put this up here is that, again, there's other ways to figure this out. There's actually a couple of different ways to do the logic here, but up here, these red cells are either a 7, 1 or a 5, 3. And whatever one they are is going to impact down here. Now, if these are a 7, 1, that 1 is gone, which means that becomes a 9. And down here, you have a 3, 4, 5 triple. And again, because of the the negative constraint on consecutive digits, you can never have 3 digits in a row because one pair of the two of those is always going to be next to each other. No matter what you do, if I make this one the 3, well, in this case, that could never be the 5. And then that 4 would always be next to the 5. No matter what, with a string of 3 digits, you can never have the 3 consecutive digits next to each other. So that basically is just one way of showing that this can never be the 5-7 pair, or the 7-1 pair. This always has to be the 5-3. And then again, that ripples through. That has to be the 7. That has to be the 1. Now we know that the red digits here are the same as up here, so that can never be a 1-7. That can never be a 1-7. Now we have just some cleanup to do. This can't be the 1-7 here. That's a 5-9. We have a 3 in the box now, so none of these ever could be a 3. No. And then these can never be a 1. And we're kind of narrowing things down from here. We have a 3-5 pair in the box, so this one has to be a 9. So that eliminates that from being the 9. 4-7 pair in the box, because of the 3-5. All right, this can never be a 4 because a 4 is in between the 3 and the 5. So that gives us the 7 there, the 4 there. Oh, again, because of the 2-6, I think I mentioned before that you can never have a 3 next to the 2-6. So that's actually makes that one the 5, makes that one the 3, makes that one the 3. And, we're kind of off and running. Now, this can never be the 6 because it's consecutive with a 3. We've determined before that that couldn't be the 6, so that leaves the 6 up here at the top. Leaves us with the 1-8-9 pair up here. Again, let's clean up here the 5s. That can't be the 3 or the 5. All right, now let's see. I know that there's an easy way to distinguish from here on out. So let's fill in the rest. Let's see, 3, 6, 5. I don't see any simple constraints that I can't do there. 1, 4, 7, 9, 1, 9 up there. And then, so let's fill in our possible candidates down here. So we have a 3, 4, 7, 6. So this can be a 1, 2, 5, 8, 9. The middle one has to be, or there has to be a 2 down here. So that middle one can't be a 1. Next to a 4, you can't have the 5. And then these 3 are actually a little bit easier. So that's got to be a 3, 6, 8. If I'm looking at this right, 3, 6, 8. All right, so the 3, 6 are always going to be a 2-to-1 ratio. So you have to put the 8 in the middle to keep those two apart. So that gives you the 3, 6 on the ends, but that means that this one can't be an 8. Oh, we should have known that from up here, since those two are always going to be an 8. Sorry about that. So I can delete 8 as a combination there. And since that's an 8, we then can't have the 7, 9 here at the bottom. You can't have a 4 adjacent to the 8, so that's got to be the 1. Now that bounces up to the top here. That's how I eliminate the, I couldn't remember exactly how I did that. So that up there at the top has to be the 9. That gives us a 1-8 pair. Gives us a 4-7 pair there. That can't be the 1. That can't be the 2 because it's next to the 1. 2926. I know that there's a way that I can reduce this down to the final digits. What am I missing here? 4, 7, 4. Oh, yeah, there it is. 2 can't be next to the 4. So that gives that the 9, makes that the 5, makes that the 2. The 2 can't be next to the 4, makes that the 7, makes that the 4. 4 can't be next to the 3, gives you a 6 there and a 3 there. So basically that fills out almost the whole column. Now they have a 5, can't be next to the 6, so gives us a 2 there and a 6 there. Like I said before, I'm not going to go through the entire puzzle. I just wanted to kind of show some of that beginning logic. Now the rest of that can be used to fill out the rest of the grid. And there is a couple of pretty tricky steps that you need to do. If I go ahead and fill in all the potentials for this candidate, for this column, the only thing we have there is a 3. So let me just fill in 1, 2, 4, 5, 6, 7, 8, 9. This can't be a 6, 4, 9. That can't be the 2, 5. This can't be the 7. 1, 8. 4, 6, 9. Again, 4, 6, 9 here as well. 1, 5, 8. 2, 7. So those are the ones that can be eliminated just from Sudoku of not, of having a conflict in the rows and columns. However, again, you have a 4 there. 4 can never go next to a 2, can't go next to a 5, can't go next to an 8. 2 can't go next to a 1 or a 4. 7 can't go next to a 6 or an 8. 1 can't go next to a 2, but the 3 can't go next to a 4 or a 6. 3 can't go next to the 2. 9 can't go next to the 8. 6 can't go next to the 5 or 7. 8 can't go next to the 4, 7, or 9. And then 3 can't go next to the 4 or 6. So as you fill that through the rest of the grid, you can fill in, this column. There are, like I said, there are a couple of still fairly tricky steps left where you have to basically, use some pretty hardcore logic to, you have pointing pairs, so this ends up being 2 numbers and that ends up being the same 2 numbers, so that eliminates those 2 numbers from being in the rest of the column. For example, if I remember right, there was one easy step here. Yes, the only one of these that can be a 4 is this cell here, because 4 is now eliminated from everywhere else in this row. That one has to be the 4. And again, now that eliminates the, the 8 next to it, the 5 next to it here. So it's just kind of going through that regular old Sudoku logic, with the negative constraints of the consecutive digits and the 2-to-1 ratio. But that does give you everything that you need to fill out the rest of the puzzle. Hopefully this has been informative, possibly entertaining. I don't know. But if you do manage to solve the rest of the puzzle, I'd love for you to go onto the Logic Masters Germany website, fill in the answer that that says that you've been able to solve the puzzle. Go ahead and give me a rating. All of the puzzles on Logic Master Germany have a rating for the rating of how nice the puzzle is and then difficulty level. So, this, my one I did a couple of weeks ago, Moriarty Leaves a Clue, has a 4-star difficulty and a 93% rating, which is actually pretty good. Any puzzle that has that is a pretty nice puzzle. So thank you so much for your time, and we'll see you on the next video. Thank you. Bye-bye.